Okay, well, welcome to the first interdisciplinary colloquium of the new year. Today, we're very happy to welcome Dr. Katrin Heitmann from Argonne National Laboratory. Before that, Katrin spent many years at Los Alamos National Laboratory, actually. She's an expert on high-performance computing as well as cosmology, and her specialty is going to use and develop some of the largest computer simulations of partial formation. And to do that, she's been a major user of several of the most powerful supercomputers available in the world over a number of years. And at present, she is actually the coordinator of the simulations and computation group of the LSST Dark Energy Science Collaboration. We're very fortunate that we have somebody who's so deeply involved in both these efforts at the forefront of supercomputing and cosmology, and we look forward to hearing from her about the dark universe.
Thanks very much. A little bit like in January, it's overcrowded because everybody has New Year's resolutions. So it looks a little bit like this. So thank you very much for the nice introduction. I had a very good day here at Northwestern today already. And so what I'm going to talk to you about is a little bit about the dark universe that was promised in the abstract. I will also talk to you about HACC. HACC stands for Hardware Hybrid Accelerated Cosmology Code. At Argonne, our management always refuses to say HACC is the real name. They say that doesn't sound very scientific, but it actually describes the code pretty well, so we are very proud of it. So HACC is our computational cosmology code, and you will see a lot about it in the background. It's actually one of the simulations. And then at the end, I will talk a little bit about HACC science, and in particular what we are doing with the HACC simulations as part of LSST, the Large Synoptic Survey Telescope these days. When I reread the abstract, I was a little bit worried that I promised you too much, so I might not hit all the points in there, but if you have questions afterwards, what I didn't explain from the abstract. So this is an interdisciplinary colloquium, so I want to first give thanks to many collaborators. And what you should notice here is that I marked them with yellow, red, and blue frames, and those stand for different disciplines. So the blue guys are the statisticians, the red guys are computer scientists, and the yellow guys are the physicists and cosmologists in the field. And I must say, like, in order to use these very large supercomputers and do these simulations, and also interpret them afterwards, having these interdisciplinary collaborations is extremely important. And being at the National Lab, I had really the fortune to meet a lot of these people and have the opportunity to work with them. So I think that is something that will become even more important in the future of the field, but is already. So let me first give you a quick introduction to the dark universe. So cosmology compared to physics, so this is for the non-physicists in the audience. In physics, what we do is we do experiments. So we have some phenomenon that we want to study, we build something that is very focused on what we want to see, and we try to understand it. And repeat the experiment several times so we can get good statistics. But in cosmology, that's not the way how it works. What we do in cosmology instead is we are making maps. So we are making maps of the universe, and these maps we make in different wavebands. So what you see here is an X-ray map, a map in the microwave background, a map in the optical, a map in the gamma ray. Then what we try to do is we try to interpret each of these maps by themselves, but we also try to cross-correlate the information from the different maps in order to really find out what the universe is made of and how it evolved. And these maps can be very, very large. The Slow Digital Sky Survey is a survey that we call it more than 500 million objects, many billions, will be recorded with LSST, for example. So this is clearly something that involves a lot of data. We statistically analyze these sky maps, and what we also need for analyzing these maps is large-scale computing. We need the computing for the analysis itself, as well as for making predictions that we can compare our observational data to. And this is something I just show in almost every that we talk about, that we make this a little darker. This is actually not that new, but I still like to show this. This is data from SDSS. And the reason why I like to show this is what I want to show you is the range of data that we have. So this is really what you see here is a sea of galaxies that SDSS over the years observed. And so we are going to zoom into a very specific point, into this point. And so what you see here is actually a merger of two galaxies. And so the big question that we have to answer, and that we have, is a big challenge that we have in computational cosmology, is that we want to simulate the very large scales, the distributions of the galaxies, and we want to go to the small scales that you see here. So this, as you can imagine, is actually not an easy thing to do, and so this is kind of what this talk will be about. And again, for the non-astronomers and cosmologists in the audience, I just want to put up some numbers about sizes. So when we have an optical survey, like what LSST will carry out, it covers roughly 4 gigaparsec cubed, and the parsec is 3.26 light years, or 31 trillion kilometers. And the number of galaxies in the survey can be in the tens of billions. And the intergalactic separation of these galaxies is roughly a megaparsec. We have 4,000 megaparsecs in volume, and galaxies are typically separated by a megaparsec. The mass associated with these bright galaxies is 10 to the 11 to 10 to the 13. And when I say mass here, it's the dark mass as well as the light mass, but the dark mass is actually dominating. The typical galaxy size itself is in the 100 kiloparsec, and so what you see from this, you go from 4 gigaparsec to a megaparsec to 100 kiloparsec. So this is 6 orders of magnitude, and that's what we want to simulate. So we have to get the full volume in our cosmological simulations as well as the resolution that we see down here. So this is our task. What have we learned so far from the data? So the one thing that we have learned, the universe is really dark. So only 5% of the matter in the universe is actually visible matter, and only 0.5% is in stars. So the rest is in something which we call a dark energy. So this was observed the first time in 1998 by looking at supernovae. And it's this weird phenomenon. If you think about it, if you throw a ball in the air and set it down again, it just accelerates further and further. So we want to find out what this is all about. And that is kind of like at the heart of the research that I am doing, dark energy. So we want to know what is it, why is it important now? If we would have lived a couple billion years earlier, we wouldn't have seen it. Interesting. So we want to characterize it better, and that's why we are doing big observations to come up with a possible explanation. The other component is dark matter. So observations show us that 27% of the matter in the universe is dark. That means it doesn't emit or absorb light. And so we see it indirectly right now. We are trying these very large experiments to actually find out exactly what dark matter is. But so 95% of the universe is dark. We do not understand the nature of it, the origin of dark energy and dark matter. And this is really what cosmology is about these days. The other thing that we have gotten a really astoundingly good handle on is the evolution of the universe. So here you see a cartoon of the evolution. So we start somewhere here with the Big Bang 30 billion years ago. Then we go through something that we call the dark ages. Then the first galaxies start forming. And down here we are where we are observing now. Simulations that I will show you are starting roughly when the universe was 50 million years. So the universe was still dark. It was in a regime that was almost linear, so that we actually know how to set up these. And the initial conditions are informed by the observations. The interesting thing is that the dominating force in these simulations is actually gravity. We understand gravity pretty well. So we can actually carry out these simulations of the evolution of the universe, at least on large scales, quite nicely. This is one slide about the equations that we solve. So as I said, gravity dominates on large scales, so that's quite nice. So the physics is not too complicated. We use particles as traces of the dark matter in the universe. So typically, a particle in our simulation has the mass of 10 to the 9. Remember at the start I told you that the mass connected to a galaxy is 10 to the 11. So something that represents a galaxy in our simulation is represented by the halo that surrounds this galaxy. The particle mass is given by the volume and the number of particles that you can stuff into your simulation. So you want the biggest supercomputers because you want to have this number, the volume is given to you because you want to simulate the survey, so it's 4 gigaparsec. So you want to stuff as many particles into the computer as possible to get the resolution down. So you get a small particle mass so that you resolve things. On smaller scales, you also have to add gas physics, and there are people here at Northwestern, Jordane's group, for example, who do a really, really great job, but I'm not going to talk about that. So I'm really focusing on the larger scales where gravity dominates. One very interesting quote from Bob Dickey from 1969 is that he said, "The universe is far too complicated a structure to be studied deductively, starting from initial conditions, solving the equations of motion." But this is exactly what we do today on the computer. We start from the initial conditions, we evolve them forward, and we actually see things that make sense. So the equations are pretty quickly described here. So it's the Vlasov-Poisson equation set. So what you see here is, so A is the expansion factor that describes the expansion of the universe. Here you see the dark energy component, the piece. Here you see the matter piece, which is the dark matter content, so the 27% that I was talking about. And this is the equation of motion for these tracer particles that we want to simulate. So in a nutshell, what do we have to do in order to cook up our universe? We have to know about the constituents. So we have figured that out pretty nicely. We have to have the dynamical rules, gravity rules. I showed you the equations that we have to solve. We have to set up the initial conditions. At the beginning, everything was nice and Gaussian, so we can do that as well. And we need a very big computer. The bigger, the better. And here's how it looks like. So what you see here is actually a small piece, and it will evolve when I click again. At the very, very early start. So this is roughly thousands of the whole simulation, and I just picked that out so that you can actually see in a second much better what's happening there. And what you see here is that everything is very smooth. So this is the initial condition we start with in the almost linear regime, almost Gaussian. You don't see almost anything. If you had like, you could come very, very close, you would see that there are very, very small fluctuations, small overdensities in there. And gravity will start and take these overdensities and enhance them. So matter will go towards these small fluctuations. And that's what you see here now. You see here all these structures are actually forming. So Z is redshift, it's a measure of time. So we live at Z of 0, so we are going very closely. And so you see here all these structures that form. And so what you should think about, so what you see here is a movie of the dark matter evolving under gravity, taking into account the dark energy. And so in each of these clumps now, if we would have hydrodynamics in there, galaxies would start forming. Depending on how heavy these clumps are, more galaxies would form. Like here you see something that will pose the whole cluster of galaxies. So many hundreds of galaxies would live in here. But this is the dark matter distribution that we can generate in the computer. So now what would happen if I changed the constituents? So at the beginning I told you I have 27% dark matter, I have like 70% dark energy. What would happen if I changed it? So this is the dark matter distribution from a simulation that was done with the standard model that I described to you. So now imagine I say like, somebody in the audience says, but I don't believe dark energy. Throwing the ball in the air just sounds crazy, please take it out. So I can do that, and I can run this forward again, and I see what happens. So what you see here is that the matter, the structures, are much clumpier. And so the colors in here are velocities. So the redder it is, the faster the particles are moving. So you see that the structure is actually quite different. So now we can say, okay, maybe dark energy is there, but maybe cold dark matter is actually something different. Can you change the properties in the cold dark matter? And I can do that as well. I can give it a little bit of a temperature. So I did that here. I simulated, again, from the same initial conditions, but with this extra component in the dark matter being warm. And you see that the structures get very much washed out. So you can really learn a lot about these different models from simulations. And one thing that you also want to do, that I'm not going to talk about today, is you want to know what happens in between. So for that, our group developed something called cosmic emulators, but again, I don't have time to talk about this right now, but it's another very interesting topic. So the one thing that we know is that these two are already ruled out. So we know the structure is not clumping as much as it is here, and we also know it's not as much as smooth as it is. So I gave them to you because you can actually visually see differences. But now, you should ask immediately this question. You actually don't see the dark matter with the telescope directly. You see it indirectly through weak lensing. But in general, what we observe are the galaxies. So we observe the distribution of the galaxies of the time. And what you see here is kind of a cartoonish picture of how we are going from this dark matter distribution that I just showed you to compare it to actual observations that we are taking with. So we start off with a supercomputer. This one is Titan. It's a supercomputer at Oak Ridge. Some call it an old lady because the supercomputer is already 5 years old. It was used to generate this dark matter distribution. And then what you are asking is, so you can zoom into this, and you see that all these small little substructures. And now you can say, okay, if I have a substructure of this kind, of a certain size, formed at a certain time, I assume that a certain galaxy will light up in it. And this makes kind of sense because gas will fall into the dark matter potential wells, then it will start heating up and form galaxies. And so let's take this model as a given. I give you the masses, so those I can obviously, from the simulation, I just can count the particles that are in each cup. I can determine the mass. And I'm telling you, if I have a mass of, I don't know, 10 to the 11, there's at least one galaxy. So I do that, and I produce a catalog that looks like this. It's a little hard to see, but they're actually galaxies. Then I take a telescope. So this is a slow digital sky telescope again. It's a 2-meter telescope in New Mexico. It was very close to Los Alamos where I worked, so kind of I have a connection to it. And those people in the audience who know me know Salman, who is actually a theorist staring at this telescope. He's also my husband. And it's actually quite interesting when theorists go to the telescope. The observer people make very, very sure that you don't touch anything. So he has his hand in his pocket for good. Anyway, so now you measure the distribution of these galaxies. So this is a 2-point function. So you measure from each galaxy the distance to the next galaxy pair. And you plot that up. And so you see here in black are the measured data from the slow digital sky survey. See there's a small little median here, so that's very nice. And now you measure the same thing from the simulation. So you measure it first from the dark matter simulation only, so the density. That is this red dashed line. And then you say, but really I wanted to do the galaxy modeling on top, so you can do that. You can actually see that you can nicely do this. So now again you can go back to the same thing on these other simulations that I showed you, and you will find that you cannot match easily the simulation without dark energy. So this is actually pretty impressive. The other thing that I want to quickly show you is, so this is SDSS. So this is what LSST will see. It's exactly the same field of view. It was actually done with the deep lens survey, which has roughly the same resolution as LSST. And so you see there's a lot more stuff going on. So the one thing that tells you is that the resolution in these simulations has to increase by a lot because I have to get these very small structures that host my galaxies. But also analyzing these the observational data will be much harder as well. A lot of things are going on here that I think we will have a lot of fun with in the next decade this year. So this was a really short tour through through the dark universe. Now I want to tell you the hack story. So I told you what we can do with these big simulations, but now how do we produce it? And so this is really something, so the next little bit is probably more interesting for the computing-oriented people. And so I grew up in Germany, so I love fairy tales, I grew up with them. And so this is kind of like the hack story told in kind of a fairy tale thing. So it started in the Southwest once upon a time in 2008, so 10, 11 years ago, with a machine called Roadrunner. And so the Roadrunner story is actually quite interesting. So in December 2007, we got an email from the person who is responsible, or who was responsible, he's retired now, for the computing overall at Los Alamos. And Los Alamos is a very big lab. It's like 3 times bigger as Argonne. So computing is a big deal. And Los Alamos had this interesting idea that it wanted to have the fastest supercomputer in the world, and that they wanted to break the petaflop barriers. That was a big deal in these days. That nobody had been able to build a supercomputer that is that fast. So just to put this into some kind of thing that you work every day with, so a petaflop is roughly 200,000 laptops. And so the one kind of slightly crazy idea that they had was to do this with cell accelerators. So the cell at the time lived in the Sony PlayStation. So they worked with Sony to actually take this accelerator and put it into a supercomputer. A lot of people said this machine is a crazy architecture. So Andy White said it's forward-looking, not crazy. And he was actually right. And the problem was that basically there were no codes that could run on this machine. So you build this machine, fastest machine in the world, and nobody can run on it. That seems pretty silly. And so Los Alamos management decided that people who are working in basic science, they are poor. The weaponeers are basically saying, don't even come with this machine. Los Alamos is a weapons lab. And they said, we don't want a machine that we can't use, but these basic scientists might be crazy enough to take on this challenge, to write codes that can run on this machine, and they have access to this machine, right? I mean, as a cosmologist, you don't have that often access to, especially in 2008, to the fastest machine in the world. And so they said, we give you some funding to write this code, and we give you 6 months on the machine. We select like a handful of projects, so you really get a lot of science done. And are you willing to do that? Cosmologists are poor, as many of you in the audience know, so we said, yeah, sure. We will try that. And out came something that is called MC3, Mesh-Based Cosmology Code on the Cell. So after the cell was gone, we had to rename it, so it morphed into Hack. And MC3 was actually based on MC2, which was a particle mesh code written in high-performance Fortran, quite different from what we have. And so this is a slide I always like to show. So I'm reading every morning a newspaper in German, it's the Süddeutsche. And they had an article on this machine. And so it's nice because I could actually send my mother a thing saying, hey, look, the stuff that I'm doing is in the newspaper. A couple of things I want to point out. So one is Germans, in the German language, you always have genders. So the supercomputer is he. So if you work on a computer and the computer doesn't work and it's he, it's much easier to curse at that thing. I curse a lot at it. Another thing I want to point out is that my American colleagues always make fun of the long German words. So here's an example, Atombombenexplosion, which is basically, and guess what it is. But it also said cosmology. It said, it leads by example, technology of the future. And that was actually true. And I'll come back to that. And so now, here we are. This is us. How can we use? And here is the computer scientist who is really excited, like a weird architecture and more stuff like this will come up in the future, exascale, so they don't want to hear about us. But as computational scientists, we also have to do science with the code that we write, and we can't afford to rewrite a code all the time. So we wanted to actually create a code that would work on this machine for the 6 months. But after that, we didn't want to throw this code away. We wanted to make sure that we can use it. And just for fun, because actually Roadrunner is kind of similar to the modern GPU-enhanced systems, here's kind of what the challenge was. So the challenge was the following. These pink guys here are the cell accelerators from the Sony PlayStation. And they are the things that do all the computing. So they're really fast. They're like the GPUs in modern GPU computing. The blue guys here are the normal CPU systems. And the one thing on Roadrunner that you can see is that the memory on the CPU layer is the same as on the cell accelerator. So when you put your simulation on this computer, you want to make use of both layers with regard to the memory, and you want to make very good use with regard to the speed of the cells. The other problem that you see is that in a simulation, the particles talk to each other across the whole machine. So what you can see here is, and again, it's the same problem with the GPU machines, that's why I'm explaining this a little bit more. If your particles sit here on these pink guys, they can't directly talk to these pink guys. They actually have to go to the blue guys, and the blue guys have to talk, and then you can send them out to the pink guys. So this is slow. So if you want to have a really fast simulation that makes really good use of these cell accelerators, we want to avoid having going down this way all the time. So that's important. So what's important is the opteron. So this blue layer has a lot of memory. You don't want to throw that away. The cells dominate the compute, but they don't communicate well with each other. And the last thing that I haven't told you yet, but that is also important, is that the cells had a new programming language. So Fortran or C didn't work on them, so it's called cell intrinsic. It's something that doesn't even exist anymore. So what we wanted to do was we wanted to come up with a code that had a very simple thing living on the cells. So if we had to replace it with something else that could run then on a different computing architecture, we wouldn't try too hard that we have to throw away the cell code. So that was important. We had to make sure that we use both parts of the memory, and we also had to give the cells a lot of communication limited work. So those were the things when we started designing this code. And we wanted to make sure that this code will run on future architectures. We did not just want to write it forward. And this is like on one slide what we came up with. So what you see here is kind of the top layer of the code that lives on these blue guys, on the CPU component. And so each of these squares is kind of descriptive of a node. So what we did was we actually invented a passive zone so that each node actually had a little bit of information from the neighboring node. The one thing that you should remember in cosmology is when you saw this evolution, these particles don't zoom across the box like crazy. They evolve slowly. So a particle that lives on this node will not end up on this node. Will not travel more than 30 megaparsec during its lifetime. So that's good. So you don't have to worry that things go from here to here. So you just have to worry that you can understand what's happening on the neighborhood. Then, so that's the first thing. So in order to overcome this question about the communication, you put in these extra layers. Then the second thing that you do is you split up the force calculation. So what you have to do in these simulations is calculate the gravity force, and you split it up between a long-range force, which lives on the CPUs and which does all the communication, and a short-range force that lives on the cell accelerator. And so this gives you the speed. And you put that all together, you do some adaptive time stepping analysis on the fly, what kind of things, and you actually come up with a code that works really, really well on this. Here's just a really old picture from 2008, where I managed the code run for the first time on the full machine on Roadrunner. The reason why I'm showing here a telephone picture is that the machine was actually in a classified area. I'm a German citizen, I couldn't go there. So I was really sitting on the phone with them. So I was calling them up saying, I'm starting the simulation now, can you please take a look? And you actually have to watch these machines. Pretty amazing. So this all worked out quite nicely. These are scaling plots just to show that the code was doing what it was supposed to do. And here's a comparison of our code with the standard code that cosmologists know and love. It's called Gadget. And both codes agreed at the better than 0.5% level, so we were very happy with this. And so yeah, we had a new cosmology code that was actually running very nicely on Roadrunner. Then the story continues, and our group moved actually to the Midwest. And the Midwest has a supercomputer, it's still there, it's called MIRA. And MIRA is quite different, very different from Roadrunner. So MIRA, in order to get the computational power it needs, it doesn't have accelerators. Instead, it has many, many, many cores, called a many core machine. And the question was, can our code that we have now really be ported easily to architecture? And we had to make some adjustments. We had to change the long-range solver a little bit. And we had to replace the cell kernel that we had written with a tree algorithm that was tailored to the region. The nice thing was that we could isolate this short-range solver very nicely and give it to somebody who helped us a lot, who's actually sitting here, Vitaly Morozov. He is a performance engineer. And so we actually were able to, in a couple of months, get this thing running on many core machine, which was really, really nice. This was actually something that made it to a Gordon Bell finalist. Only the computer scientists in the audience would care. But we got almost 70% of peak performance. The thing scaled out to more than 1.5 million cores. And again, it worked really nicely. So we kind of had shown that all this thought that we had put in when we designed the code from scratch. And this is something that we had to make a decision about. Like, we really had to make a decision, do we want to start a code from scratch or not for this challenge? And it turned out to be actually quite successful. Then from there, we went to the south, Titan. You see the old lady already. You see, Americans make them feminine, I think. And so here it was actually quite interesting. So the one challenge that we had is, if you know about GPUs have less memory than the cells. So we had to deal with that a little bit. So we had to make sure that we stream the data nicely. And I had some nice discussions at lunch about this. And we again had to change the computing language. So now we had to go from the cell intrinsic, something that's called OpenCL. Those of you who have programmed on the GPU know that NVIDIA actually prefers CUDA over OpenCL. So after some time, we actually did replace the OpenCL kernels with CUDA kernels. But again, this kind of shows you that our whole strategy of designing the code to have this one kernel, short-range kernel that lives on the cell, on the GPU, to be easily replaceable worked out really well. I did not mention this, but I should have when I described hack. 95% of the code keeps completely unchanged when we move from one architecture to the next. So it's only 5% of the code that we have to tune to these new architectures, and that is relatively straightforward. Again, we tried to win the Gordon Bell Prize. We made it finally again. We got 20 petaflops of peak performance on Titan, quite nice. And again, things happen. And we travel one more time, actually travel now to the west and back home, and go to the next architecture, which is called the Knight's Landing architecture, or for short KNL. And I'm sure you're already all bored hearing about this very only time. So what we decided at this point was actually to add more physics to the code. So the KNL code, we actually decided to start and writing hydrodynamic code. I'm not going to talk about this. But basically what you see here is the dark matter density from the test problem and the baryonic density. And the whole design structure of hack just lends itself extremely well to it. So now not only do you stream the short-range solver or the dark matter through the GPUs, for example, but also baryons. So the new name of this code is track hack. So then people were like, you really are not serious about what you are doing. This time it was not my fault. The hack was my fault. Track hack was a stupid. And let me make it just dark one more time. But I love movies. So this is actually now the temperature of the baryon in a simulation that we carried out on the KNL. So what you see here is the formation of a cluster in the center again, and some temperature evolution. And the white stuff is actually the density. So you see how things fly in and out. So now the code has much more physics, much more fun things to do this. But for the rest of the talk, I will actually predict the gravity only. So this last piece of the journey actually happened over the holiday break. So I told several of you already about this. But so Summit was delivered. Summit is right now the fastest supercomputer in the world. It's 200 petaflops. So 1 petaflop on Roadrunner, 200 petaflops now at Oak Ridge. And the computer was assembled last year. And just before the Christmas, like on the 21st of December, I got this question from Oak Ridge if I would be interested in running our code like 24/7 on the machine to stress test the machine. And I said, yes, I want to do that. So literally for the break from the 21st to the 3rd of January, I had this whole machine for myself. It was pretty amazing. I mean, other people probably think I'm a little stupid, but that the biggest thing in my holidays is that I can run on this computer. But we actually generated 3 very nice simulations, and this is just a picture of one of them. So we are analyzing them right now. So I was really excited. So it took us literally 1 afternoon to get the code up and running. So that was really nice. So the Python version was just transported over. You have to always tweak the settings of the machine a little bit, but it basically ran out of the box. And this is just hacking pictures. So the one thing that we have done, and I in particular, we have been the first users of machines several times, and it's always kind of interesting. So some it worked really well. Some machines don't work very well at the beginning, and so this one is actually the award that our team got, and this is at that time Eric Isaacs was the director at Argonne, and so we discovered that something was wrong with the machine. So it's kind of interesting. So we had this new code that I tried to run. And so I ran the code on pieces of the machine, not on the full machine at first, and I looked at the output. I ran literally the same code with the same input. And the outputs had some weird spikes in some of the cases. And if you just wrote a new code, you think like, yeah, you are silly, you made this bug in your code, right? So I was kind of like disappointed because I thought, okay, this stuff. And I just did this one thing that I ran this thing over and over again and see what happened. And sometimes I had a spike and sometimes I didn't. Then I went to Vitaly, who you saw in this other picture, and I said, like, I don't understand this. I mean, usually bugs don't look like this. And it turned out that it was actually a hardware problem. And so we discovered that before signed a contract with IBM that everything was good. So IBM had to fix the hardware. And so that's why we got an award, because Argonne got money for that. Down here is a picture that shows us Gordon Bell. So Gordon Bell is the guy who puts out the money for the Gordon Bell Prize. And the one, so I'm here, you almost. The one very sad thing about this picture is that I'm the only woman in this picture. And I think that definitely has to change. Our group at Argonne, we have lots of women in the group, so I'm excited about it. But I think really this is something. So physics is bad, but computer science is. And this is just, so this was MC squared, the nice hot run code that we started with, that ran on normal machines. Down came all these different architectures. And now we have this really speedy code called Hack that can take advantages from all of these machines. So sorry, this was a little bit of a long story, but it's something that occupied the last 10 years of my life quite a bit. And for me, it's always exciting to get the code to run on the machine. So let's switch a little bit now for the last 15 minutes of science that we have on this app. So this is a list of very large simulations that we have done. So one is called the outer rim simulation. So this was done on CIERA, the computer at Argonne. And so what you see here is actually the full box, and these spheres are halos above a certain mass cap. The very blurry stuff, blue stuff, there are so many halos that you can't see them all. It's just the density of these halos. And so this simulation has a 4 gigaparsec volume, so you can fill in the survey. It generated almost 5 petabytes of data. And the mass distribution, remember, 10 to the 9 was what we aimed at, so this had 2. So I'm going to talk about the simulation quite a bit, so that's why I'm describing it. We had other simulations with higher resolution, the continuum simulation suites that cover many, many different cosmologies, so you can do studies that I showed you at the start. The Borg Cube is the first hydro simulation that we did. And then over Christmas, I did these 3 Star Trek planet simulations. They each have almost 2 trillion particles, so double the size of this one. And it's pretty amazing also in December when I did the Outer Rim simulation in 2012. I mean, it took weeks. And this stuff just ran in a couple of days. So you're like, wow, I should have just waited a few years and done it like that. So the kind of science that you can do is the investigation of fundamental science questions. So Hilary Child is a student with us. She has done a lot of work to just look at the properties of these things. The concentration mass relation. One of our postdocs now, me, he took the outer rim simulation and he looked at John lensing effects if you have line of sight structure in between you and the speed lens. You can also look at new probe cosmology. If you have a great new idea, you can take the simulation and try that out. Or you can do predictions for existing probes like the annual. And then you can do survey science. So this is something that I have focused on a lot in the last 18 months. So as Claude André said, I'm part of the LSST desk collaboration. And I am coordinating the simulation and computing part of that collaboration. So on paper, this collaboration has right now more than 800 collaborators. So we are using these simulations to actually investigate possible systematics. Even though they aren't data yet, but they will come. Test pipeline developments, and for that we develop full end-to-end simulations. So what I've shown you was kind of so far is the theorist view of the universe, of course, very well controlled, but we actually want to have something that looks like the real. I'll talk about that the rest of the talk. So this is a very beautiful picture. This is how LSST looks right now. So everything down here is done. Down here is the computing room. It has 8.4 meter mirror. It will survey 37 billion stars and galaxies. The survey will take 10 years. First light has a little bit of a squiggle. This is around 2020. First science data will come out. And it will also have a lot of alerts each night that people can follow up with science. And so besides the LSST project, which will deliver this data via science collaboration, one science collaboration that I am deeply involved with is the dark energy science. And so right now, we are generating simulations to test out what will happen with the real data. Here's just a picture of the LSST survey area. So LSST lives in the south Chile, and so it will survey the southern side. So right now, the plan is to do an 18,000 square degree main survey, and then deep drilling fields, 10 square degrees each, where you go really, really deep and come back many, many times. So this is slightly different science targets. And there will be annual data releases where you can look at images, objects, and sources. And everybody who lives in the US can become immediately a member of LSST and look at the data. So the data that we are going to simulate, that I'm going to show you, is actually this 100 square degree patch. And so I'm showing you to you because the simulation that we are doing is really at this patch here. It was kind of interesting for me as a theorist that how does it matter if I measure the patch here or there. And they were actually telling me, no, it matters because the heating conditions are different and want to be really accurate. And so we had to do the simulation. And DESC is doing a set of data challenges and basically end-to-end simulations. And I said this before, so we want to test analysis and processing pipelines. We want to look at mitigation strategies. What I will show you in just a few minutes is that we are actually simulating things like tensor effects. So the CCDs on LSST are not perfect, and we are simulating that. We are simulating atmospheric effects. So all of this is done, and right now, roughly 50 to 60 people are working hard on the data generation, including validation, but more people actually have started to work on it. So this is what we want to simulate. So what you see here is the LSST camera, and this is the focal plane. And this little square right here is the CC9 CC figure out. And this was actually the first thing that was done in order to design this data challenge. Somebody looked at the cadence, how the telescope will observe this 300 square degree patch. Somebody actually went into the observation database, how this will be done, and told us this is the way how LSST will observe this, and this is how you will actually see. The blue region here is a deep drilling field, so that will have a little bit more detail. And just the very, very crude version of the end-to-end pipeline. So you have an extragalactic catalog. So you take one of these simulations that I showed you, the other simulation, populated with galaxies which have shapes, colors, dust, stuff. Then you do an image simulation. This image simulation will have Milky Way stars, which we know where they are from observation. It will have dust from the Milky Way. It will have the atmosphere. It will have seeing conditions. It has the full telescope involved. It has CCD defects, cosmic rays, transients. So you go through this whole thing, and you come out with something that looks like real LSST. Then you take that data and you feed it through the EM, stands for Data Management Processing Pipeline. So this is something that the LSST project is writing right now. And so you feed it in, and then you get something that looks like the focal plane that I just showed. So we are really doing some very interesting simulations here that reproduce something that looks like real-world data.
Yes.
Our group at Argonne was deeply involved in the extragalactic catalog. So I told you at the start when you want to connect the dark matter halo with galaxies, you have to come up with a prediction for that. So call that the galaxy halo connection. And you can do that in many ways. So the perfect way would be if you could run a hydrodynamic simulation that has all the galaxies ready. At cosmological scales, we are far from that, so we are not going to do that. Instead, we are going back to these empirical models. We are actually looking at halos, at their masses, and we try to say what kind of galaxies live in. There's also an approach that is called semi-analytic modeling, where you take also the halo formation history out and you try to predict a range of galaxy properties with physics-based models. This works decently well, but not as good as we need for LSST. So what we actually have done is we married these two methods and came up with a new method. Trying to explain. But basically, we are providing a very realistic catalog with galaxies. What is very important is that the analysis working group provided a range of validation tests. So we generated this catalog, and they said, this is the data that you have to reproduce. And this data covers, if you look at halo masses, masses from 10 to the 11 all the way down to the 10 to the 15. And it's a whole range of data. So you see here the Untitled Chapter survey again, which is from the Keck telescope. So you take all of these things together and you generate this validation data set to make sure that catalogs that you provide are actually good enough for what you want. And this is something, so theorists are usually not that good at curating data. So this was something where the LSST collaboration was really, really key because we had all the expertise in one place. Once you have done that, so you have generated the extragalactic catalog, you run an image simulation. And this has to be done also on the supercomputer. So this, what you see here is actually the activities of the Argonne supercomputer data. So this sits in front of the Argonne Computing Director's office. So you can see here who is speculating. And so here we were using these image simulations to actually view stuff half of the machine. And so these image simulations, they do the full ray trace. So what you do is you go to the catalog with the galaxies, you go to each galaxy. Galaxy is the size, so therefore it has that many photons. You propagate the photon through the atmosphere, you propagate whatever comes out through the CCDs, and you generate an actual image of a galaxy, which you can see more or less here on the focal plane. And the properties that are in there it's a lot. So we have, first of all, the galaxies. I told you a lot about that. Then we have AGNs, have the stars. I thought a little bit about that. We have time-varying objects, AGN and supernovae. And then we have atmosphere, optical distortion, all of this is there. And then we also have these sensor effects. So what you can see here is actually something that the sensor effects are not taken out. So you see stripes here, which are due to imperfections on the CCD. And so the data management stack has to deal with that, has to take them out. It does that actually quite nicely. So all of this is in the simulation. You have instrument signatures, emitting cosmic rays. Here's a cosmic ray. Saturation and retrace, crosstalks, all in there. So it's really very close. It's very close to real data, but the observers are still saying it looks to. One science result I want to show you, kind of a science result, which is interesting, I think, which shows you what the simulations are really, really good for, is work that was done by François Lanous, who is a postdoc right now at Berkeley. And so one worry that LSST has is something called blending. So this is actually a simulation, but it looks very much like now. So what you see here is this big bad galaxy. And then you see here these splotches. Actually, I don't know if I should make it a little bit darker again. So you see here a splotch. And now the DM stack has to decide, is this splotch a galaxy, or does it belong just to the outer part of this? So it has to do something which is called blending. It has to decide, are you a galaxy, or are you an object from a galaxy? And when this was tried out, the algorithm for deciding this on HSC, what was found that the settings in the DM stack were actually not correcting for this enough. And I'm showing you the simulation data, but could show you in the backup slides the observational data and looks exactly the same. What they found in HSC data is this blip here. So this is the I-band resolution, so these are the galaxies here. And this blip is because the DM stack identified it as a galaxy, even though it's not. It's actually really a splotch of this thing. The simulation, you know what it is because you have the tools. So you can say, okay, DM stack actually is done. So you change the settings in the DM stack and you get this here, blended with one. So you get this orange line and everything's good. But what I want to show you is this, is that you can really reproduce the data of the same quality that a telescope like HSC is showing, and getting the same problems that then can be fixed. So we have now a very, very well-controlled data set that you can use to actually investigate these. So it's really useful. And just to summarize, exciting times for cosmology, a lot of stuff's going on. We have a lot of great data already. We are collecting much more. We need large-scale precision simulations to actually really analyze the data and exploring different cosmological models. The supercomputers are there. Using them is not easy, but I think with HACC we actually made a big jump forward with that. And so HACC was really designed for high performance, but still easy portability. So if a new machine comes on the market, you should be able to run on it. Besides the code itself, a lot of work was done with respect to the analysis tool. So I didn't show this that much, but running the simulation is one thing, getting the science out of it is another thing. That's mostly done by the postdoctoral students. It's also a lot of challenging for them because they have to write code that actually can handle the big simulations. They also have to write scalable code. Very often the Python codes don't do it. So that's kind of an interesting question. We started with the baryons, lots more work to do. Lord Andre will visit Argonne for an extended time to help us with that. And so we have really started in the community to do these data challenges where we do full end-to-end image simulation to generate something that looks like the real data. And it's not to do for interdisciplinarity, as you can imagine. There's a lot of I didn't say the word machine learning the whole talk, but I could have talked to you also a little bit about machine learning efforts that are going. Some of these things, finding objects in the data, lots of things to do. And this was the last picture, because it's a pretty one. So this is actually when we took the simulated data that we have made for LSST and gave it some colors to the real image, those all of these galaxies. It's not quite LSST depth in this particular case because it was a test simulation, but I think it's already pretty nice, and I, as a theorist, can basically not distinguish. Thank you.
Thank you very much for this fantastic talk. And we have time for some questions.
So just to clarify, aside from the baryonic simulations, all of these simulations are strictly dark energy and dark matter, based on dark energy and dark matter.
So we have other stuff on the too. So what I didn't show you, for example, neutrinos in some of our new simulations. And so that was one of the business simulations we ran that had neutrinos in it. There are efforts to do dark energy crystallography. We have not done that, but other groups have done modified gravity instead of dark. So we can do things like that. So
you haven't done any modified gravity simulation?
Exactly. And there are two reasons for that. One reason is that they're all ugly. So we couldn't get ourselves to pick one because they all don't seem natural, and they are very costly. And there's a little bit more, but so the numerical approach that you have to take includes another grid solve, makes it really costly if you want to have the resolution of the simulation. So you have an ugly model and an extremely costly simulation. So you have not.
So is your intuition about dark matter then that mod's heading nowhere? Is that modified gravity is heading nowhere? Or do you think we not know enough at this stage?
I think we don't know enough. On the other hand, the gravitational waves have excluded a whole range of models, so that's kind of interesting. I know that people are still trying to get on this and still find some other corners. I don't know. I'm extremely excited about the data that we see, and we'll see some people things come up. I think there you first want to see like really in the observations, then we'll get the target to see, rather than having a theoretical study where you were trying to guess.
You mentioned that a lot of once you have the simulations, the extraction of science and the analysis is done by students and postdocs science within astrophysics. Was the coding mainly done by and with computer scientists? And can you talk a little bit about that collaboration, both how it worked, challenges, etc.?
So it's a mix. So the one thing that once we identify very, very talented students going to postdocs, we had a handful of them go all the way through with us. But actually, no, they were postdocs with us. We just studied that they were students. And then they became staff members in the computer division at Argonne. So this is kind of an interesting way how it happened. So they got deeply involved in the code. There's this idea of they would become staff members in the computer unit. They wouldn't have to worry too much about like this metrics and all publishing.
There's a lot of focus on the coding.
Right. So we had our team, I would say, and now we have actually somebody who was a computer science grad student here at Northwestern, who now postdoc, I think. The other two were physicists. One astrophysicist, one photo. So that's one way. So you keep these guys because it's very rare field and they have to commit. The other thing that we have done is, so at Los Alamos as well as at Argonne, we had computer scientists. The way how that was done was, first of all, it's much easier if you have the same institution. Actually, thought like when we were working with Vitaly Morozov on the Goldenberg thing for we met on a daily basis. But what we did for him was we identified a very, very specific part of the code where we said, this is a part where the code spends a lot of time. So he didn't have to understand first, right? He just one piece and understand. And then he said, like, you guys taking a square root, you must do right? Things like that. Yeah. But it's a different formula. So we really helped in tracking the pieces of code that needed attention. And so that there's a hybrid code, the same thing is happening right now. We have a postdoc. And so the postdoc was getting 7 kernels from the hybrid code. It's with them, he's profiling them. He's giving reports, he's saying it's not good. And then there are also questions of like the force laws, right? Can you write it? Which is really good enough, which is a polynomial instead of the square root. Yeah. And so you discuss these things. So the performance engineer tells you these are the things that you try to avoid, and then you say, okay, back to thing. And we are writing a lot of papers to do that as well. So this is the thing that you also have to, like, we are writing papers to supercomputers. Nobody has to. Basically. But it's important for them to just feel that we are working with them a trust, right? That we are not just handing work over to them. Yeah. So yeah, I spend time on this, and it's actually fun.
The other question? Yeah.
Operation.
No, I'm not. I mean, so first of all, the Hubble deep field is up in space, right? So the atmosphere is not there. That helps so much. So the seeing is so much. So the biggest difference, if you think about it, about LSST and the Hubble Space Telescope is that Hubble Space Telescope we do very specific observations of very specific fields. Like what LSST is trying to do is to survey these 18,000 square meters over and over and take images of what. But if you would compare like virtual deep field picture, it's so much more beautiful and so much clearer. It's like, so I have very bad eyes, right? So it's for me like taking off my glasses and looking at it.
Take one last question. I have your
I remember like hearing like when you were presenting about how like there's more numbers of particles that you have, like the more complex and the model you can go. I was just wondering what the difference would be running this on a supercomputer versus like a quantum computer where you can run these just really massive problems.
Very good question. So right now the problem is with quantum computers is that you only have very few algorithms that you can actually run on them. So I wouldn't even know how to start my simulation implementation. That would be the very first.
thank you, Katrin.